Gotta find the right place to put this thing in there. There, that'll work. All right. We're good?
Yes, sir.
Okay. All right, well, welcome. How are we all doing tonight? Fantastic? Good. What questions do we have?
What's your middle name?
Ebenezer.
How do you say it in code?
You.
Yeah, that's wrong, Rick, buddy.
That could be that too. But, anyway, anybody look at hamstudy.org this week? All right. How you, getting 80, 90, 100%?
I do it on the way home every day.
Oh, okay.
That's the way to do it.
A little bit a day. That works well. All right. Well, we're going to finish off some antenna stuff tonight and some feed line stuff. And I don't know what else we'll get into. We'll get into some radio equipment, all kinds of fun stuff tonight. So, but if you have questions along the way, let me know. And Brian, can you catch that light right behind you? And Rick, can you catch that one right behind you? That might make this a little bit easier to see. A little harder to keep notes, but a little easier to see. All right. So, dipole antenna. Anybody ever heard of a dipole? Okay, you've heard of a dipole. Anybody else heard of a dipole? Okay, Randy has. Well, it is the simplest type of antenna. How do I know that? Because this thing says so. But it is a very simple type of antenna. And there's a lot of folks that build them, and they're very easy to build, is my understanding. So we're going to talk about them just a little bit. So when we talk about a dipole, it basically means two electrical parts. So a pole has to do with electrical parts. You know, we switch is a pole, right? We talked about that a couple of weeks ago, and die is a couple of them. So it's two electrical parts. And it's made from a straight conductor of wire that's a half wavelength long with a feed point somewhere along the antenna. So you can have it fed in the center, you can have it off center, you can do it a lot of different ways. You can, so most of them are horizontally set up, okay? So you have a feed point, and then you have your two wires coming out from your insulator in the middle. But that's only one way that you can do it. You can also have them installed vertically. You can have them sloping, even drooping from a single support in the middle, which are known as an inverted V. What do you think it'd be called, an inverted V? It's what it looks like, right? Yeah. Okay. And they're actually fairly easy to put up, and it's an inverted V. Okay. The radiation pattern is isolated in space. It looks like a donut. So not much in the middle, but around the edges. Now there's another kind of antenna known as a ground plane antenna. Now this is Kyle's favorite kind of antenna because he's an air traffic controller and he likes it when the planes get onto the ground. You was wondering how I was going to tie that in, weren't you? He likes the verticals. Going straight up. Yeah, we're going to talk about safety in a few weeks, and we're going to use this guy as an example. He did. He didn't want to talk about that tonight. Okay, so the most common type of a ground plane antenna is a quarter wave long with the feed point at the base. Okay, so a ground plane antenna, I've got one sitting in my house. I have a ground plane antenna. And the feed point is right at the bottom of the antenna. And it's vertical, goes up 22 feet, something like that. And it acts like a half wave of a dipole with the missing portion made up by the electrical mirror formed by the ground plane. So I got a picture to kind of help explain that, because that just sounds a little crazy, right? So if you got a dipole, you got two electrical parts, right? Now a ground plane, you got one electrical part that might be your vertical, your other electrical part is your ground plane. And your ground plane can be made up of multiple things. Well, I was going to bring my new ground plane. I forgot it tonight. I'll bring it next week. It's actually some cloth. Faraday cloth. You seen those? Got to try it. It was got my, huh? You stay with your wires? Okay. Or you can have wires going out from the bottom of your antenna, which makes up the other portion of your dipole.
How long do the wires have to be?
That's a good question, and it depends on what bands you want that dipole to radiate on. So
How long does it need to be compared to a vertical one? Usually it's a quarter wave.
Yep.
You got half wave up with quarter wave out, like quarter wave on band again.
So the vertical part would be a quarter wave and then
It's a half wave.
oh, that would be,
They're high. Verticals are usually quite high.
and then the ground wires would be a quarter wave.
Or quarter wave. And you usually run more. You've got 16 on yours?
yeah, I've got, yeah, 16 I'm running, I think, wires. So I've got ground plane wires going out in all directions around my antenna. They're 32 feet long, and I've got about 16 of them up.
And when you tune that antenna, you get your standing wave ratio.
Mhm.
You tune the ones on the ground or the vertical one?
Usually the ground. No, and it depends an awful lot on the ground, the conductivity, soil. You know, there's a guy that does a lot of YouTube videos. He throws a wire in the ocean. He uses the salt water as his ground. But the better your soil is, real dry, sandy soil is not a good conductor at all. But a nice, soft, wet soil works excellent.
And you had said you were going to use a Faraday cloth to try it.
Yep.
So how big does the cloth have to be a quarter wave?
Nope, it does not. In fact, there's a couple of guys out there that have tried this, and they've also tried a window screen for a ground plane. So if you think of a window screen that you would put on your sliding glass door, right, for a deck, about that big. So it's not that, it's not huge, and you can tie right into that, and that becomes your ground plane. So there's a lot of different things that you can do. You can use individual wires. You can use something like that. People are trying things all the time to come up with new ideas.
Absolutely amazing to see that when they started talking about that. Instead of putting out, a dozen wires, usually if you're on 40 meters, you want wires around that, 30, 35 feet. You got this little window screen, which is half the size of that cable. Put in the center, put your antenna in the middle, make sure you ground it, and it works like a charm. The latch is, and it's easy to roll around.
Okay. So it would be portable.
It's extremely portable.
Yep.
And Jeff talked about the Faraday cloth.
The Faraday cloth will fold up into a packet about that big. And it's soft. It's just like cloth, but it's got copper embedded in the cloth. And so it just came in the mail from Amazon a couple of days ago. So I'm anxious to to get out and try it and see how it works. I'm going to use it on the Wolf River coil. It's basically a portable type antenna, and that's a little vertical. So I'm going to give that a shot. So it's a lot of fun. You can play with a lot of things. Okay. Okay, so as we talk about ground plane antennas, the extended length of about 5/8 of a wave ground plane focuses more energy towards the horizon to get a better range. So it depends on where you want your wires. You can actually get some direction in those antennas if you focus them in a certain direction. Except if you focus them towards the pine tree on the corner of my lot that's on my neighbor's yard, doesn't help. I've tried that. Doesn't help. Okay, so to reduce the physical size of the antenna, it's often constructed with some radiating conductor wound into a coil or a separate inductor inserted into the antenna called an inductive loading. So if you think about a half wave, it's pretty long, right? And if I'm going to put a half wave up there for 40 meters, I'm going to have a vertical 60-some feet up. And if I go for 80 meters, it's going to be, twice that, 120 feet. Well, I could not get my wife to agree with me putting up a 120-foot antenna. There's just no way. But you can put a coil within that antenna, and that allows you to bring the length of it down, because that coil is part of the radiating part of that. And so it allows you to physically shorten that antenna. Now, there's some compromises that go with that, but those antennas work very well, and they're very well designed. And so that's the inductive loading. You're able to shorten the length of those antennas and still come up with something that's going to work very good as far as receiving and transmitting your signal.
A real common one we use for a 20-meter antenna is 17 feet, 17-foot width. It goes onto a small coil.
Yep.
And the ground plane underneath it, and it will virtually all bands, so 80 meters.
Yeah, and it will. And within your coil, I have one. It's called the Wolf River coil. Coil's about this big, this tall, right? About this big around. And it's got a slider on the outside, and you move that up and down the coil, and that can change which band you're working. So it shortens that coil up or lengthens the coil as needed, and then it allows that coil to work on different bands. So this is basically a picture of a ground plane antenna. And as we look at this, we have the actual wire or the radiating element here in a vertical position. And the ground plane is down here, okay, on the ground. And it's basically, here's half of our dipole going this direction, and the other half is down here as the ground plane. And so you still have the two parts to your antenna, but one is here and the other one is using the ground as part of that antenna. You can get them at multiple ways. You can have them so your radials are coming off this way. They can be above the ground, or they can be stretched out around your antenna. This is the way mine is at home. I've got it stretched out, coming out from the center, and I've got 16 of these going around my antenna. And yeah, they're 32. Yep, 32 footers. And when I put them out on top of the grass, and I just used landscaping stakes to hold them down. And now after a year, you wouldn't even know they're there. The grass has grown over them, and which is good because my kids will not hit them with the lawnmower. I hit one with the lawnmower the first year I had them out, but still works. So this is, you know, how if we look at a regular dipole, which is the picture over here on the very left, in the center, you got an insulator, and you've got one wire going one direction, you got one wire going the other direction, and this is where your antenna is going to be fed, is right here in the center. Okay, so another type of radio is a handheld. We've got a couple of examples here. Randy's got a Yaesu here, and I've got just a couple of GMRS radios. And these radios here have what is known as a rubber duck antenna. Why do you think they call it a rubber duck? It doesn't quack, I'll give you that, okay? I hope it doesn't quack. It's made out of rubber, right? Wires are inside of this rubber covering, and so it's known as a rubber duck. The distance on one of these radios, depending on how much power you've got, it's not all that far. I mean, you can get to the repeater from here, but with this radio you can.
Yeah.
With these, probably not. These have a little less power than that one does. Okay, so it depends on how much power you're running, exactly how far you're going to be able to get. But the better the antenna, even on a handheld, the better transmission and the better reception that you're going to get. So the flexible antenna used with most handheld radios is it's called a rubber duck. The ground plane antenna is shortened by coiling the conductor inside a plastic coating. Here's your plastic coating, right? Here's your coil down in here, okay? You can see that it's a little bit thicker down here. Let me pass this around.
Just a little bit.
Yep, that's a good idea.
Turn that thing on and start screaming.
Yeah, you can do that, but it's both dead. I turned them on. I was hoping I had some power in them, but not tonight. I don't. This one, I don't know which version this one is. It's GMRS. That's. But. No.
I don't expect a lot of Bluetooth support here. There is some.
So here's a Baofeng, and you're gonna hear a lot of people talk about Baofeng. Some people will say Baofeng is the worst thing ever invented, and there's some people who will swear by these. But these are good little radios, and they work, and they work very well. You're not going to have them working inside this building, okay? Because the building is made of metal, okay? It's a Faraday cage. They won't work so good inside your vehicle, but if you have an antenna on top of your vehicle, and you take this antenna off, and you hook that other antenna on that's through a piece of coax, it'll work. And these will work very well. We have a...
Vice President has that set up.
Yep.
In his vehicle. Works like a chair.
It does. He's using 5 watts with it off the top of his vehicle, and it works very well.
I would say too, Jeff talked about Baofengs. I love the fan that says it's probably one of the greatest radios ever made. It's because they're extremely inexpensive.
Yes.
They do everything inexpensive.
They will. They will do anything an expensive radio will do. You just don't have the power.
You don't have the bells and whistles.
But this will transmit, this will receive, and it'll cost you about $30. Okay?
I'd love to know how many AM operators started.
A lot. That's how they start out, with just a handheld.
The Yaesu, that's an FE70. That is a digital radio. So that'll do the VHF, UHF plus digital. That will do fusion. So you can talk virtually anywhere in the world on that radio going through the internet. Those run a little over $100.
Yeah.
It's not extremely expensive, but it's a good radio start.
But I listen to the System Fusion Digital often as I drive to work and what have you. And, you know, I hear guys with these handhelds all the time getting on there. And they're able to communicate around the world on a digital radio. Just
With a technician license.
with a technician's license. Somebody's playing with the generator.
Okay.
Okay, so it doesn't transmit or receive as well as a full-size ground plane antenna. For best performance, hold the transceiver so that the antenna is vertical, okay? And why do you think that would be? Why would I want to, talk into this radio with the antenna in a vertical position? Any idea?
Well, if that thing is acting like a ground plane, you want a vertical element.
Yeah, exactly. That's exactly what you're going to say, wasn't it? All right. Well, you were going to say?
That like actually.
Bingo, yeah. So if you've got Rick over here that has another one, if he's holding his like this, and I'm holding one like this, not so good, right?
Especially if I'm turning this way.
Especially if he's turned the other way, right? But if they're both oriented the same direction, it's a better chance of this antenna talking to that antenna. The radiation pattern, they will cause them to pick each other up. Great point. Great point. Okay. So they're not very hold it vertically. They're not very effective inside vehicles, up to 20 times less effective than an external mobile antenna. That's quite a difference, right? And I found that out when I started using mine. I put it in the car and this thing it's a worthless radio. I can't get out of it. I rolled down the window and I put my head out. Can you hear me now? It worked a little better, except then you got the wind noise, right? Yeah. So, but an external mobile antenna works very well. Okay? And it's easy to connect handhelds to full-size antenna. They use a standard RF connector. And so a 5-watt handheld, this is 5 watts, right? With a good antenna, it can reach up to 10 miles. That's not bad. That is not bad. Okay? Okay. Well, another thing that we need to talk about a little bit is how long does that antenna length need to be? That's Brian's question earlier. How long does this need to be? So, to calculate the length of a resonant dipole, a half wavelength long, there's a formula. And it is 468 divided by the frequency. Okay? In megahertz. Or 468 divided by F. Now that's the formula for a half-wave dipole. So for example, at 50.1 megahertz, which is in the 6-meter band, the dipole length is calculated as 468 divided by 50.1, which comes out to be 9.33 feet or 112 inches long. Okay?
If you make it a dipole, you cut it in half.
If you make it a dipole, you cut that 933 in half. So that ends up being 4 point something.
56 inches on each side. 4 foot 8 inches.
4 foot 8 inches.
Unless you're doing off center fit, then you do 1/3.
We haven't got to that part yet.
Okay, I'm sorry.
Okay. So note that the value of the constant used in the formula accounts for the effects that cause an antenna to act like a little longer electrically than it is physically. So the actual resonant length is affected by the height above the ground, its electrical properties, and thereby conductive objects, and so forth. So these antennas can be affected by the atmosphere around us, what is around us. So at 468, which is the constant, it accounts for that. And so you make the dipole a few percent longer at first. So you want to use like 490 instead of 468, and then you use an SWR meter to determine what length you actually need. It's always a good idea if you're making an antenna, if you're building an antenna, to build it a little bit longer than what you think you need, because it is easier to cut a little bit off than it is to add. Okay? So always cut it a little bit long and then shorten it up as you use your SWR meters to determine the exact length that will bring it right into resonance for your desired band. So how about the ground plane length? Calculating ground plane length. So the length of a ground plane antenna is half that of a dipole and is often estimated as 234 divided by the frequency. Okay? So for example, at 146 megahertz, which is in the 2 meter band, okay, a quarter wave ground plane is 234 divided by 146, which is 1.6 feet or 19 and a half inches long. So if you're going to build you a 2 meter antenna, it doesn't have to be very long. 19 and a quarter inches long for the wire for that antenna, which isn't that long. And Randy has one of those in the back, I think. So he'll bring that out.
A little over 3 feet.
Yep. And you can talk on it. So length adjustments also apply similar to, when we were talking about the dipole. It's a little bit longer. You want a little bit longer, and then you can shorten it up and bring it into adjustment. Now, how do you keep notes on the top of that bottle cap?
That's a quarter wave. Lip mount antenna mounts in the back of your truck or trunk. But that's the length.
Yeah, so that's not very long at all. All right. So another type of antenna is a directional antenna. So simple dipoles, ground planes, and loops work very well, but they don't have a lot of gain, but they have very little gain, especially in one direction. They're omnidirectional, but if you want to put some definite power in one direction or another, you want to get a directional antenna, okay? And so often you use a directional beam antenna to get the best reception in one direction. So if I want to take an antenna and I want to reach Southern California from here, my vertical will do it, but my vertical is going to get out probably the East Coast, West Coast. I may not be sending as much of my power in one direction. In fact, my power is going out every which way. But if I get a directional beam antenna, I can beam that power in one direction. So like, beam me up, Scotty. Now what's that from? What do you guys think that's from? Beam me up, Scotty. I know your dad knows that. Star Trek. So, but, yeah, get that beam going in one direction. So on VHF and UHF, if a direct signal path is blocked, a beam antenna can be used to aim the signal at a reflecting surface to bypass the obstruction. So if I want to get around that tree that's sitting there as an obstruction, and I'm on 2 meters, or I'm on VHF, UHF, 2 meter being in that area, I could get a directional antenna and I could not be able to bounce it off my neighbor's house. You never know. So you can do some crazy things with radio waves. So the most widely typed of beam antenna is known as a Yagi, and I know we brought the Yagi antennas out before, but that's the most widely typed of beam. And they have much more gain than the omnidirectionals in the preferred direction. Okay? So this is the Smith chart on a half-power Yagi. Okay, it's a 3-element Yagi with a driven element, and we see that that it's going out here in one direction, coming out up here towards the top. That's where most of that power is going, in one direction. And you can get dish antennas. You can get all kinds of different Yagi antennas. They can be horizontally polarized. They're the ones that you usually use for long distance communications. They have lower ground losses than when the wave reflects from or travels along the ground. You can get a long way on those. So as the frequency increases and the size of the Yagi elements becomes smaller, it becomes more difficult to construct practical antennas. That's why you get dish antennas above 1 gigahertz, because they become practical at that point. A Yagi is not so much. Okay, as your frequency changes and increases, the Yagi elements they just won't cut it. So that's where you get that dish element, the dish antennas. So I ever wondered why they can hit the satellites? You get Dish Network or Direct TV. Their radio signals going up to the satellites. Just happen to be bringing in video. Yeah, you can send TV signals across the radio waves, even with a regular radio. It's called slow scan TV. I've never played with it. Randy, you ever play with?
A little bit, yes. It's you got to be right on the satellite, but it's really interesting to be able to see a picture coming down from outer space.
So yeah, a lot of things you can play with. All right, looks like we got some questions here. So which of the following describes a type of antenna loading? Electrically lengthening by inserting inductors in radiating elements, inserting a resistor in the radiating portion of an antenna to make it resonant, installing a spring in the base of a mobile antenna to make it more flexible, or strengthening the radiating elements of a beam antenna to better resist wind damage. What do you think? It is electrically lengthening by inserting inductors. So this is where you're electrically lengthening your antenna by putting those inductors in the radiating element.
This one right here is a rolling coil. White coil. This coil.
6 meter, 2 meters.
Okay, yeah, why don't you come show that, Rick?
Just basic. Stripping the coax, taking off the shielding. Now this is for 6 meter, but it also works on 140 and 70 centimeter. Cool part is there's the 70 centimeter. copper tin. Just hang her up, and I put this on a fiberglass pole about 30 feet in the air.
So you can make antennas that work and can look strange, but they work.
And it doesn't cost a whole lot of money.
And it doesn't cost a whole lot of money. Yeah, that's right. All right, which of the following describes a simple dipole-oriented parallel to the Earth's surface? A ground wave antenna, a horizontally polarized antenna, a traveling wave antenna, or a vertically polarized antenna? I think it would probably be B, yeah, because it's horizontal parallel to the Earth's surface, so that would be horizontal, right? Yep, excellent. Okay, what is the disadvantage of the short, flexible antenna supplied with most handheld receivers compared to a full-size quarter wave antenna? It has low efficiency, it transmits only circular polarized signals, and it's mechanically fragile. What do you think?
A.
It is A. It has low efficiency. So it's not as efficient as the bigger antennas. Which of the following increases the resonant frequency of a dipole antenna? Lengthening it, inserting coils in series with radiating wires, shortening it, or adding capacitive loading to the ends of the radiating wires? It is actually C, shortening it. So as we increase, which of the following increases the resonant frequency of the dipole antenna? We shorten the dipole so that the frequency is going up.
All right, increment antennas and all, they'll always say, cut them off.
Yep.
Same plan with the same amount of power, but putting it into a smaller place.
Yes. Exactly.
Kind of right here.
All right. What is the disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle? Signal strength is reduced due to the shielding effect of the vehicle. That sounds good, doesn't it? A, yeah. And what is the approximate length in inches of a quarter wave vertical antenna for 146 megahertz?
I know.
I'm sure you do. She's getting it calculated, I can tell. It's in inches. So it's 234 divided by 146, right? Let's see.
You showed that. Actually, it's 19.
Well, we're not going to go to the quarter, yeah.
That's approximate.
It's approximate, yeah. So here, what is the approximate length in inches of a half-wave 6-meter dipole? Okay, so we're half-wave, right? So the formula is what? 468
I just brought one in.
divided by, now 6 meter, we're looking for megahertz, right? So 6 meters is 50 megahertz. So we got 468 divided by 50-ish.
50.1.
So in inches, what would that be? 112. Yep, that is correct.
That is probably the most useful formula you will ever use. I've been doing this almost 40 years, and I use that every time I make an antenna. I use that. It's a good one to keep in mind.
Yeah. It definitely helps on when you're making antennas. That way you can come up with the length. In which direction does a half-wave dipole antenna radiate the strongest signals? Okay, so we got a half-wave dipole, right? It's fed in the center. It's got its two electrical elements. So is it equally in all directions, which would be omnidirectional, off the ends of the antenna, which if you got your antenna, it'd be coming off the ends of those wires, in the direction of the feed line, which is basically back towards the ground, or broadside to the antenna. So if your antenna is sitting this direction, broadside would be coming out this way. What do you think? D, broadside to the antenna. That is correct. Okay, and what is the advantage of a 5/8 wavelength whip antenna for a VHF or UHF mobile service? It has more gain than a quarter wavelength antenna. It radiates at a very high angle. It eliminates distortion caused by reflected signals. It has 10 times the power gain of a quarter wave antenna. What do you think? It is A. It has more gain than a quarter wave antenna. So it's a bit longer, right? So it's going to have more gain. Okay, what antenna polarization is normally used for long distance CW and single sideband contacts on the VHF and UHF bands?
Randy knows.
I do.
But I bet we have some others that might have an idea. So we're looking for long distance in the VHF and UHF bands. It's actually going to be C, because we're going to be horizontal to the Earth. Okay, and by being horizontal to the Earth, we can get some ground plane helping that signal go along. All right, when using a directional antenna, how might your station be able to communicate with a distance repeater if buildings or obstructions are blocking the direct line of sight path? Change from vertical to horizontal polarization. Try to find a path that reflects signals to the repeater. Try the long path, or increase the antenna SWR. Do not do D.
I like that.
Do not do D, Rick. Don't do it. You'll be smoking that radio. All right, what do you think? B. Yeah. Try to find something that reflects the signal, and you might be able to bounce it over to the repeater. You get there. So if you got a hill in the way, try to bounce around the hill. That's how Randy gets around the hill sometimes, I bet. It's gotta be. All right, and what is a beam antenna? An antenna built from aluminum I-beams? Oh boy. An omnidirectional antenna invented by Clarence Beam? An antenna that concentrates signals in one direction, or an antenna that reverses the phase of received signals? That is a mouthful. But if you look at the answers, do you see how you can eliminate some of them? It is C, yeah. That is correct. Yeah. So, aluminum I-beams.
Rick, we could blow one, buddy.
I'm on it. But I just want to know, is Clarence, is that Jim's brother?
Yeah, it is. Younger brother.
All right. Which of the following types of antennas offers the greatest gain? A 5/8 wave vertical, an isotropic, a J-pole, or a Yagi? Yagi, yes, exactly. Okay, so we have antennas. Well, we have to feed them with something, right? We talked a little bit about this last time, but here's a table of some of the common types of coax cable. Their impedance, the loss per 100 feet, and at 30 megahertz, and the loss per 100 feet at 150 megahertz. So as we look at this, if you look at this right off the bat, which kind would you just kind of start not wanting to use? Just you're looking at impedance alone.
RG59 and RG6.
Yeah, because you want something that's going to have an impedance of about 50, right? Because that's what our radios love, is they love that 50. Okay, and then we see, some of these have better loss ratios than others. Okay, so if we look at RG8, 100 loss per 100 feet is 1.1. Okay, 8X at 30 megahertz is 2.0. Okay, now if we really want to get so we have low loss on both at 30 megahertz and at 150 megahertz, which one would we choose? LMR 400. And that's the thick stuff, okay? And it's also a little pricey. But, there's some of this other stuff that works very well. RG8X, I use RG8X all the time. And I find that it works very well. It's easy to work with. And you can put ends on it very easily. And I did that a couple of weeks ago. Tinkered around with it, put some ends on some. And, but it's good. But by the same token, if you are trying to reduce your loss, you might want to go with something like an RG213. And you'll get, less loss than what you would on an RG8X. Okay? So it just depends on what you're going to use, how long your run's going to be. The longer you run, you want to get a better coax because you're going to be able to have less loss.
I do have some 174.
Use that light, Kyle. Light. Right. Perfect. Thank you.
That is RG174. And you see the diameter, right?
Yep. Very thin.
It's very, very small. RG 174.
I ain't never seen that.
Now, even though this has high loss, it's extremely light. And this is 20 feet, so I don't have much loss to use it. I run mostly in low power, so it works really well for that. Now, if you want to put it up 100 feet at the VHF levels, I'm losing 10 dB. So most of our signal from the radio going up top is lost to the cable. So the thicker the cable, the better you are for VHF.
Yeah, so if we were to run that at at 100 feet, right, at 150 megahertz, we're not going to be getting any signal out of that antenna. Okay, it's just not going to happen. And that's not what you want. So with that, you'd want to go with something else. RG8X would work. LMR 400 would be better. But you're going to have trade-offs with whatever you want to do. You might trade off a little bit of money for a better signal, or you may be able to get an acceptable signal for a little less money. It just depends on what you want to do.
LMR doesn't cut you any slack in me.
No, it's horrible to work with.
Yeah, it's very, very difficult to bend and get it the way you want it to go.
The difference in losses between the 213 and the 400 really is negligible. And it's a little bit cheaper and it's much easier.
Yep. So if you're trying to get something with low loss and you're thinking between RG213 and LMR 400, you might want to consider the 213. It's just easier to work with and you're not losing that much. Exactly. All right. Coax cable called coax. The performance of coax cable depends on the integrity of its outer jacket. And moisture contamination is the most common cause of coax failure. So you want to make sure you keep the coax from getting moisture in it. And so when you have, you know, like my antenna, it's up on the roof. It's going to get rain up there. Whoa! That could get into coax. What could I do to stop that from happening? Waterproof it! Yes! Waterproof it. How might I do that?
Super glue.
Super glue? Yep, there are different types of tape. I've got one that's a moisture barrier tape that I put on mine, and that will keep the moisture out of there. You can use electrical tape.
But the cable itself or just the connection?
The connections.
Yeah.
Yep.
The cable itself is
The cable itself is protected. You don't just, where the water's going to get in, it's going to get in that connection, and you don't want that getting into your
covered.
yep.
My friend does AV stuff for work. Today he was telling me that a customer had to go up to the low tower and replace the coax. Somehow water got inside the braid. And it whipped it all the way down, so he cut the bottom of the water, started pouring out of the coax.
Yeah. So if you don't have it watertight,
Yeah.
you can definitely get some damage going on. You don't want that to happen. Okay. So prolonged exposure to ultraviolet light and sunlight will cause the plastic in the jacket to degrade, it cracks, then moisture. And so some coax jackets use a pigment to absorb and block the UV. And so if you can get it where you're getting some UV protection in that plastic, you're better off. Because over time, what the coax look like, Kyle, when you took it down off of your tower, what your dad had up there?
Nasty.
Cracked and
Pretty rotted,
yeah. So that'll happen over time.
yeah.
Yeah, so his dad had it up there a long time, but over time it will happen. And coax should not be bent sharply. You can short center conductor to the outer braid. If you turn it and get it too sharp, you don't want to do that. You don't want to have a short circuit there. And there's a lot of different kinds of connectors that you can use with coax. Okay, this is kind of a sampling of them. You have N-type connectors. You can get BNC. You can get BNC to N's. You can get BNC to BNC. You can get UHF to UHF. All kinds of things. So there's adapters and all kinds of different connectors that you can use and put on the coax. Just depending on what you're going to use it for, what your radios require, and for instance, the handheld. You can't put a regular coax connector on that handheld. It takes a different kind of connector. Okay? So, but you can get the adapters so you can get it to hook up to those. So, the type of connector to use depends on the signal frequency. And UHF series connectors, the PL259 plugs and the SO239 receptacles are the most widely used in the HF equipment. So you'll hear that all the time. You'll hear the PL259 or the SO239s, and those get used often.
BNC is probably the next.
And BNC is probably the next one, and they're very easy to use and very fast to put on and off.
And you'll see that some instances, like on Amazon, it'll say UHF cable. It's not just for UHF. It'll cover all. They just use it as a name.
Yeah, and just to make note here, UHF in this case does not stand for ultra high frequency, okay? So when we're talking about coax, it's the type of connector, it's not the ultra high frequency that we talk about when we're talking about radio waves. So above 400 megahertz, the type N connectors are used. And water and coax cables degrades the effectiveness of the braided shield and increases the losses. And in low loss air core or open cell foam coax, special techniques are required to prevent water absorption. So they make it a little bit harder on that solid core stuff to keep them watertight. There are ways, and they have their ways to do that. Okay, so let's talk just a little bit. You ready?
Yeah, I'm ready.
Okay. I thought I shocked her for a minute. All right, so we're going to talk a little bit about SWR meters and watt meters. So an SWR meter, we like to measure our SWR in our antennas and our coax cable. And it's important that we make sure that our SWR is within an acceptable range. So using this type of equipment is very important. So SWR meters measure the SWR by placing them in series with the feed line, usually right at the output of the radio. So you can put one of these meters between your radio and your antenna, and it'll give you constantly what your SWRs are running. Many radios have built-in SWR meters, and my radio, when I look at it, I've got an SWR meter, and I can tell when I'm transmitting what my SWR is on my antenna. And you always want to make sure that it's not getting too high. So alternately, a directional watt meter can be used to measure SWR. You measure the power flowing towards the antenna and the power reflected by rotating a sensing element or turning a switch. So there are a couple of ways to do that. You can also get an antenna tuner. And an antenna tuner, the impedance, also known as impedance matchers or trans matchers or antenna tuners, are used if the SWR at the end of the feed line is too high for the radio to operate properly. That doesn't change the tuning of the antenna, but it changes the match coming to your radio. So your radio is happy with it, but your radio is not going to be as efficient as if you have a one-to-one match between your antenna system and your transmitter. So most tuners combine the function of impedance matcher, directional watt meter, and antenna switch. So they're all kind of all in there in that tuner. I've got an external tuner with my radio, and does the trick. So if I've got it's a safety precaution is what I use it for. In case that SWR for some reason gets too high, it will stop me from transmitting if I have to, or it will bring the match together. And so an automatic tuner sense when the SWR is high and make the necessary adjustments, and that's what mine does. It automatically senses that. You can get an antenna analyzer, and there's many types of antenna analyzers. Randy's got one up here that he uses. So this is an antenna analyzer. You put it on the antenna, and it'll tell you what your SWR is, as well as what your impedance is, and all kinds of different information. So that's one way. And here's another antenna analyzer. It's a little thing, almost like a deck of cards, right? Does the same thing as this. Very complicated to use, this little one. I've got one similar to this, and I got this one first, and I got the other one second. I'll use the other one. But it only goes, for me, Mine only goes up to 6 meter. Mine goes up to 6 meter.
Yours go 6?
Mine will go 6. But I can't get up to the UHF and the VHF with this one. With this one, I can't get up to UHF, VHF, but this one will get up there for me. So if I'm checking out my UHF and VHF antenna, I use this one. If I'm checking out my HF antennas, I'll use this one. Okay? But these are very handy, and it helps to ensure that your SWR is where you want it to be. Okay? Any questions on that? All right. So they're used to manage your antenna systems without using a transmitter whose signal might cause interference. So you just hook it up to the antenna. You don't have to use your transmitter, your transceiver, when checking out your antenna. All right, we've got some practice questions. Which of the following causes failures of coax cables? A, yes, moisture. Okay, why should the outer jacket of coax cable be resistant to ultraviolet light? Yes, D, can cause damage and allow water to enter the line, right? What is the disadvantage of air core coax cable when compared to foam or solid dielectric types? Yeah, C, it requires special techniques to prevent moisture in the cable. And which of the following types of solder should not be used for radio and electronic applications? We didn't talk about this one, so we're going to learn something here. Acid. A? Acid core solder should not be used. Okay. Makes sense. The others are conductors, aren't they?
Acid core will do some damage.
Uh-huh. You don't want acid. Okay, what is the characteristic appearance of a cold tin lead solder joint? Okay, I'm hearing B or C, and it is C. Yeah. Yeah, she's got that down. A rough or lumpy surface. There we go. Which of the following RF connector types is the most suitable for frequencies above 400 megahertz?
B.
It is B. It's a type N. And which of the following is true of PL259 type coax connectors? C is correct, yes. And which of the following is a source of loss in coax feed lines?
D.
It is D. It's all of those. Water, high SWR, and multiple connectors in the line. So as you go through different number of connectors, you lose something each time you're going through one of them. Okay, what is the electrical difference between RG58 and RG213 coax cable? What do you think? Any? Yeah, it is C. Good guess. Educated guess, though. Has less loss at a given frequency. Okay. And where should an RF power meter be installed? In the feed line between the transmitter and the antenna, at the power supply output, in parallel with the push-to-talk line and the antenna in the power supply cable as close as possible to the radio.
I like,
A.
I like it.
Yeah, in the feed line between the transmitter and the antenna. So we have to think about what kind of power are we measuring? We're measuring the RF power, right? That's what the power that's going to go out on the antenna. So we want to be between the transmitter that we're sending the power to the antenna and the antenna. That tells us how much power is going to that antenna. Yeah, see, it's pretty funny. They come up with some interesting options on these tests. So, which of the following is used to determine if an antenna is resonant at the desired operating frequency? B. Yes, that is B. It's an antenna analyzer. And which instrument can be used to determine SWR? I heard D. Directional watt meter. Yep, very true. And what is the major function of an antenna tuner? An antenna coupler is also known. It matches the antenna system impedance to the transceiver's output impedance. It helps the receiver automatically tune in weak stations. It allows an antenna to be used on both transmit and receive, and automatically selects the proper antenna for the frequency band. A, that is correct. Yeah, it would be nice. Okay, well, this is the end of Module 4. We're going to take up Module 5, but I think we need a break. At the output of the radio, so you can put one of these meters between your radio and your antenna, and it'll give you constantly what your SWR is running. Many radios have built-in SWR meters, and my radio, when I look at it, I've got an SWR meter, and I can tell when I'm transmitting what my SWR is on my antenna. And you always want to make sure that it's not getting too high. So, alternately, a directional watt meter can be used to measure SWR. You measure the power flowing towards the antenna and the power reflected by rotating a sensing element or turning a switch. So there are a couple of ways to do that. You can also get an antenna tuner. And an antenna tuner, the impedance, also known as impedance matchers or trans matchers or antenna tuners, are used if the SWR at the end of the feed line is too high for the radio to operate properly. That doesn't change the tuning of the antenna, but it changes the match coming to your radio. So your radio is happy with it, but your radio is not going to be as efficient as if you have a one-to-one match between your antenna system and your transmitter. So most tuners combine the function of impedance matcher, directional watt meter, and antenna switch. So they're all kind of all in there in that tuner. I've got an external tuner with my radio, and does the trick. So if I've got it's a safety precaution is what I use it for. In case that SWR for some reason gets too high, it will stop me from transmitting if I have to, or it will bring the match together. And so an automatic tuner sense when the SWR is high and make the necessary adjustments, and that's what mine does. It automatically senses that. You can get an antenna analyzer, and there's many types of antenna analyzers. Randy's got one up here that he uses. So this is an antenna analyzer. You put it on the antenna, and it'll tell you what your SWR is, as well as what your impedance is, and all kinds of different information. So that's one way. And here's another antenna analyzer. Just a little thing, almost like a deck of cards, right? Does the same thing as this. Very complicated to use, this little one. I've got one similar to this, and I got this one first, and I got the other one second. I'll use the other one. But it only goes, for me, mine only goes up to 6 meter. Mine goes up to 6 meter.
Here's go 6.
Mine will go 6. But I can't get up to the UHF and the VHF with this one. With this one, I can't get up to UHF, VHF, but this one will get up there for me. So if I'm checking out my UHF and VHF antenna, I use this one. If I'm checking out my HF antennas, I'll use this one. Okay? But these are very handy, and it helps to ensure that your SWR is where you want it to be. Okay? Any questions on that? All right. So they're used to manage your antenna systems without using a transmitter whose signal might cause interference. So you just hook it up to the antenna. You don't have to use your transmitter, your transceiver, when checking out your antenna. All right, we've got some practice questions. Which of the following causes failures of coax cables? A, yes, moisture. Okay, why should the outer jacket of coax cable be resistant to ultraviolet light? Yes, D, can cause damage and allow water to enter the line, right? What is the disadvantage of air core coax cable when compared to foam or solid dielectric types? Yeah, C, it requires special techniques to prevent moisture in the cable. And which of the following types of solder should not be used for radio and electronic applications? We didn't talk about this one, so we're going to learn something here. Acid. A? Acid core solder should not be used. Okay. Makes sense. The others are conductors, aren't they?
Acid core will do some damage.
Uh-huh. You don't want acid. Okay, what is the characteristic appearance of a cold tin lead solder joint? Okay, I'm hearing B or C, and it is C. Yeah. Yeah, she's got that down. A rough or lumpy surface. There we go. Which of the following RF connector types is the most suitable for frequencies above 400 megahertz?
B.
It is B. It's a type N. And which of the following is true of PL259 type coax connectors? C is correct, yes. And which of the following is a source of loss in coax feed lines?
B.
It is D. It's all of those. Water, high SWR, and multiple connectors in the line. So as you go through different number of connectors, you lose something each time you're going through one of them. Okay, what is the electrical difference between RG58 and RG213 coax cable? What do you think? Any? Yeah, it is C. Good guess. Educated guess, though. Has less loss at a given frequency. Okay. And where should an RF power meter be installed? In the feed line between the transmitter and the antenna, at the power supply output, in parallel with the push-to-talk line and the antenna, in the power supply cable as close as possible to the radio.
I like,
A.
I like it.
Yeah, in the feed line between the transmitter and the antenna. So we have to think about what kind of power are we measuring? We're measuring the RF power, right? That's what the power that's going to go out on the antenna. So we want to be between the transmitter that we're sending the power to the antenna and the antenna. That tells us how much power is going to that antenna. Yeah, see, it's pretty funny. They come up with some interesting options on these tests. So, which of the following is used to determine if an antenna is resonant at the desired operating frequency? B. Yes, that is B. It's an antenna analyzer. And which instrument can be used to determine SWR? I heard D. Directional watt meter. Yep, very true. And what is the major function of an antenna tuner? An antenna coupler is also known. It matches the antenna system impedance to the transceiver's output impedance. It helps the receiver automatically tune in weak stations. It allows an antenna to be used on both transmit and receive, and automatically selects the proper antenna for the frequency band. A, that is correct. Yeah, it would be nice. Okay, well, this is the end of Module 4. We're going to take up Module 5, but I think we need a break. All right, we're back on the air. Okay, so I'm going to start into give some distance into Module 5, which we're going to talk about the amateur radio equipment itself. We're going to talk about how it works, a little bit of modulation, transmitters, receivers. We'll talk a little bit about digital communications, and then, well, how in the world do you power this stuff up? And we'll talk about power supplies and batteries, the way that you can power the radios, because you can't take it over to the current bush. It just won't work.
There's a guy in Iowa that can do it.
Oh, that guy can, yeah. All right. Yep. All right, so modulation. We'll talk a little bit about modulation and bandwidth. So the basic radio station, and this is really basic, okay? We start out with, we got an antenna. And the antenna goes to the feed line, okay? Which comes down to a transceiver switch. And this dotted line around here, this is known as the transceiver. Why do you think it's called a transceiver? It transmits and it receives. Exactly. So you got a transceiver, you got a transmitter piece of that, you've got a receiver piece of that, you got a switch that determines whether I'm transmitting or I'm receiving. And you also have a power supply that's going to the transmitter and the receiver. Okay? That's the basic radio station that you will have. And it doesn't matter which radio you have, you're basically going to have these elements of the equipment. But what happens when we're communicating on the radio? We just start talking, and all of a sudden, yep. perfect. Thank you, sir. So when we have a communication for radio, how does that work? We can start talking, but unless something happens, we're not going to get out on the airwaves, are we? Rick might, but
Usually the police shows up when I don't have power.
yeah. So when we're transmitting, we're sending a signal. And what we're trying to send, either a voice, we're trying to send data, we're trying to send video, we're trying to send commands. So we take this information, whether it's in any of these forms, and we convert it into an electronic form. Then we hook this electronic form to a radio wave. And then it goes out. Okay? So the radio wave carrying the information is sent from the station antenna into space. And it's gone. We don't have to worry about it anymore. It's gone. But then we have to receive it. Or somebody's going to receive it. So we send it. We send our voice. It gets converted to an electronic signal, and it goes to the antenna and goes out into space. And then somebody at the other end is going to take that information that the radio wave is carrying, they're going to intercept it with their antenna, and they're going to extract that information from the received wave. Okay? And this information is then presented to the user in a format that can be understood, whether that is sound or it's picture, it's words on a computer screen, it's response to a command. And when we say response to a command, what do you think that would be? Okay? So if I send out a signal to a model airplane, right? Remote control airplane. That's a radio wave going out to that airplane, isn't it? So if I tell it to bank right, I'm sending it a command. It receives that command, and then it's going to bank right. Okay? In my case, it would crash. Yep, that's what it would do. Last time I flew a drone.
But what happens when you send a transmission and not receive it? It can go off the spectrum.
Until it dissipates. It does. It keeps going. All right. So what happens when we continue? So adding and extracting the information, it can be simple or it can be very complex. In my mind, I go towards the complex, even though my mind's simple. I'm thinking, how do I understand this stuff, right? So this is what really makes ham radio fun, learning about how the radio works. But don't be intimidated. You don't have to understand the science behind it. Just some of the basics, or you can get in as deep as you want, and you can learn as much as you want. You can go really deep if you want to do that, and you can learn lots of stuff. But you don't have to do that to pass the test, okay? So, if we've got our information, and we want to add it to that radio wave, we have to do something to it. And that something is called modulation. We have to modulate, whether it be our voice or whether it be a data signal or be a command, we have to modulate it so that it can be carried on that radio wave. So when we add something to the radio wave, which is also known as the carrier, we modulate the wave. For Morse code, we turn the wave on or we turn it off. Okay? And that's Morse code. Speech or music we put on there. Data we can put in there. We can modulate that. So there are different modulation techniques, and they vary with the different properties of the wave in order to add that information. So, for instance, we can change the amplitude. And that is one way we can modulate that wave. We can modulate the frequency. That's another way. Or we can modulate the phase of that radio wave. Okay, so if we're modulating the amplitude, we're modulating, how big that wave is. The frequency, what frequency are we on? Or the phase. Is it in phase? Is it out of phase? All those things we can change in order to put information into that radio wave. Now, there's a signal that doesn't carry any information. Now, if we have one of those, it is called unmodulated. So if it has no information, it's an unmodulated signal. And then when we recover information from that signal, we are demodulating that information. So we're demodulating the signal. So here's an example of continuous wave, CW, or what's it called? Morse code, right? So we have an unmodulated signal up here. So nothing happened to it, right? We have a key that we're turning on or off, and we get a dot and a dash. So if we hold it down for so long, we get a dot, let go, then we turn it back on, we can get a dash. He's going to grab a key here. Guarantee you that's what he's doing. Yep. And that is a keyer. So turn it on or turn it off. Yeah, let's play a little CW. We have an electronic keyer up here where you'll be able to hear what CW sounds like.
Okay, as Jeff said, an unmodulated signal, it's dots. So to send Jeff's name, we just said Jeff. His call is N0JFY. So that is a modulated signal. It's in dots.
So, and this is by turning that unmodulated signal on and off. Okay? Make sense? All right. Thank you, Andy. Okay.
This one does the same thing. This is a standard telegraph key. You do it by pushing on a lever. Hold it down. What happens? It's in dots. It does the same thing. It's a little different technology.
Yeah, so this technology has been around a long time.
Yes.
Almost as long as me, Kyle. Almost.
That's on the street.
So think of the day of the old telegraph lines, right? When you see those in the old Western movies. That's what the type of a key that they would use, is they would use a straight key. All right. So the simplest type of the modulation is a continuous wave turned on and off in a coded pattern, which is what we get CW. Morse code radio signals are called CW for that reason. You're adjusting that continuous wave, okay, making breaks in it. Now, amplitude modulation, also known as AM. Anybody ever hear of AM radio, right? So you have an unmodulated signal, and you modulate it by an audio tone, and you end up with your amplitude being modulated. You see how you have a higher amplitude here, shorter amplitude here? That's how that signal gets modulated, and then that can send that information out in the as a modulated signal. So in AM, the amplitude of the carrier wave is modified in step with the waveform of the information, such as the tone that's shown here. And the information is contained in the outline or the envelope of the resulting signal. So the information is carried out here on the edge of it. And it kind of makes sense because if you think about it, you know, how tall this is, how much amplitude we have, we're looking at the top and the bottom, and these are much closer together, right? So this is called the envelope. It's what's containing that signal. All right. And recovering speech or music from the envelope of the AM signal is called detection. So you're trying to detect that signal when you're dealing with AM. So it's called detection when you recover that information. Okay. Composite signals or sidebands. So as we talked earlier, there is that unmodulated signal, right? Also the carrier. So in this situation, our carrier is right here in the middle at 800 kilohertz. Well, there are two separate voice sidebands. There's one that's going from 800 to 803, and there's one that's going from 799 down to 797. One of these is called the upper sideband, which is at higher frequencies, and this is the lower sideband. It's at lower frequencies than the carrier. But this whole thing is a signal, okay? So an actual AM signal is made up of three separate signals working together. A carrier, which is right here in the middle, and two sidebands. The carrier is a steady, unmodulated signal, and the upper sideband or USB signal is the higher frequency than the carrier, and the lower sideband or LSB signal is lower in frequency than the carrier. Now, one thing to watch here is if you look, the carrier is at 800. The top of this sideband is 3 kilohertz above the carrier, and the lower sideband ends at 3 kilohertz below. And this will come into play when we start talking about where our band privileges are. Okay, we got to make sure we stay within their band privileges. So we always got to keep in mind that the carrier plus 3 kilohertz or the carrier less 3 kilohertz. We want to stay that far away from the edge of the band. So single sideband, in an AM signal, the carrier doesn't carry any information. It is the sidebands that carry that information. And each sideband carries an exact copy of that information. The upper sideband and the lower sideband, they both carry that information. But only one sideband is needed in order to transmit that information across the radio waves. So all of the single sideband's power is concentrated in one sideband. So if we put all of our power in the upper sideband, we're able to have a stronger signal, okay, by concentrating that power. And it gives us more effective long distance, and we can make weak signal contacts because of that additional power. The upper sideband is used for VHF and UHF frequencies, okay? So we're using upper sideband for the VHF and the UHF. Now both the upper sideband and the lower sideband can be used in medium frequencies and in high frequency bands, which ask a question. If both sidebands can be used in HF and medium frequency, Which one would I use? If I'm going to send on upper sideband and somebody's listening on lower sideband, are they going to hear me? Interesting question. Keep that in mind, and we'll get back to that. So modes that carry frequency of a signal to add speech or data information are called frequency modulations, or FM. Ever heard of FM radio? Yeah. That stands for frequency modulation. We're modulating the frequency. Instead of the amplitude, we're modulating the frequency. The frequency of an FM signal carries with the amplitude of the modulating signal. So it varies with the amplitude of the modulating signal. Excuse me. And phase modulation varies the signal's phase instead of changing its frequency. So in other words, it's very similar to FM, where it's dealing with the frequency and the phase of that frequency. So FM is the mode used by most VHF and UHF repeaters. So if you go out and you're hitting one of our repeaters, more than likely it's going to be an FM mode that's going to be used on that repeater. Okay? But you can also use upper sideband, but normally not with a repeater, but radio to radio. Okay? So you can use the different modes within a frequency, but you're not necessarily going to be hitting a repeater. The repeater is usually set for an FM station, or it's set for a digital station. There's a couple of different digital types that it can be set at. So, but FM is the most common. Okay, so because FM, the way the FM receivers work, only one signal can be received at a time. And this is called the capture effect. So if multiple signals are present, only the strongest will be heard in the receiver. So if Brian's sending me an FM signal and Randy's sending me an FM signal, and Brian's is stronger than Randy's, I'm going to hear Brian's. Okay? I won't hear Randy's. And you'll hear that often even on the repeaters. You'll have two people coming in at the same time, but you only hear the strongest one. So when I know that I'm going to double with somebody, I crank the power up so that I get on top of them.
Good luck with that.
That only plays a part of it. There's a lot of things that come into play with how strong that signal is. But the strongest signal is one that's going to be heard on FM. So we talked about the bandwidth of modulated signals. A signal can have both a frequency and a strength or amplitude. And signals are spread out over a range of frequencies, and this is called a bandwidth. Okay? And you can communicate with single sideband over much longer ranges and in poorer conditions than with FM or AM, particularly on VHF and UHF bands. So for even better range, extremely narrow single or CW signals are the easiest for the human operator to send and receive, especially if it's noisy or if the conditions are fading. So CW has a very narrow band, and it's easy to hear when you have weak signals. So I know Randy does a lot with CW, and he's doing it with very, very low power. And he's listening for very weak signals, and he's hearing them because CW has such a narrow bandwidth that you can hear those. Okay? And CW and single sideband are considered weak signal mode because they're more effective than FM at low signal strengths. So if you got a low signal strength, then it is definitely easier to use CW or single sideband than it is FM. So if single sideband can use either the upper or lower sideband, Which one should you use? Any thoughts? Which one should you use? Okay, upper if you're on certain frequencies. Lower if you're on other frequencies. And so there is a method out there which kind of says, if you're on these frequencies, use lower sidebands. If you're on these frequencies, use upper sideband. So the convention, that's the word I was looking for. So ham radio has standardized on the following conventions. If you're below 10 megahertz, use lower sideband. Now, if you're above 10 megahertz, which makes sense, you'd use the other one, right? Upper sideband. But there's one exception to that. If you are on the 60 meter band, which is at 5 megahertz, you use upper sideband. So 60 meters is just a special case. So if you remember, 60 meters is broken down into channels instead of the frequencies. So there's 5 channels that are on the 60 meter band, and we use upper sideband on those. All right, we'll run through these practice questions and then we will call it good for this evening. Okay, what is CW? D, another name for Morse code. That is correct. Okay, which of the following is a form of amplitude modulation? Spread spectrum, packet radio, single sideband, or phase shift keying? The answer is C, single sideband, yes. What type of modulation is commonly used for VHF packet radio transmissions? We didn't cover this one, but we'll learn. It is actually A, FM or phase modulation PM, okay? So it's used for packet radio transmissions. Okay. Which type of modulation is commonly used for VHF and UHF voice repeaters? Okay. Probably not single sideband, but that's a good thought, yeah. Probably not. Dad knows. D. Yeah. Yep, it is D. It's FM. So most of your repeaters are going to be an FM repeater on VHF and the UHF. Okay. Which of the following is a disadvantage of FM compared with single sideband? Voice quality is poor. Only one signal can be received at a time. FM signals are harder to tune. All of these are correct. B. B is correct. Only one signal can be received at a time. Which type of voice mode is often used for long-distance, weak signal contacts on the VHF and UHF band? What do you think? A long distance. We're gonna put our power right onto one side of the carrier or the other. C. So it'll be single sideband. Yeah. Okay. Which of the following types of signal has the narrowest bandwidth? C. CW. Yep. Which sideband is normally used for 10 meter HF, VHF, and UHF single sideband communication? A, upper sideband. That is right. And what is the characteristic of single sideband compared to FM? Single sideband signals are easier to tune in correctly. SSB signals are less susceptible to interference. And SSB signals have a narrower bandwidth, or all of these choices are correct. Let's see, it is correct. Single sideband have narrower bandwidth than FM. That is correct. Good. What is the approximate bandwidth of a typical single sideband voice signal? 1, 3, 6, or 15 kilohertz? So remember, we had a carrier of 800, right? The top end of it went to 803, and the bottom went to 797. So it would be B.
I say B.
All right, Rick, you got it right. So it's 3 on each side of the carrier. Okay, what is the approximate bandwidth of a VHF repeater FM voice signal? We didn't really talk about this one either, did we? A VHF repeater FM voice signal. C on this one. Between 10 and 15 kilohertz. Okay? So FM is wider, right, than single sideband, because single sideband is 3 on a side, right? So FM is wider, but not quite as wide as D. Yeah. And what is the approximate bandwidth of AM fast scan TV transmissions? And I don't expect you to know this because we didn't cover it. But it is about 6 megahertz. Okay. So AM fast scan TV transmission is about 6 megahertz. And what is the approximate bandwidth required to transmit a CW signal? He just does it. B. 150 hertz. And this is one where your answers, if you look at your answers, you got a couple of them in kilohertz, so they're going to be wider, right? And then CW is very narrow. So the narrowest one on this answer is 150 hertz. Okay? So you want the narrowest one, because that fits with CW. All right. Any questions? Next week we're going to talk about transmitters and receivers. And then we'll get into Module 6. Oh,